There's something hauntingly beautiful about the way the universe keeps its deepest secrets just out of reach. Look up at the night sky, and you're staring into an endless ocean of questions, some so profound they defy even our wildest theories. But among the countless celestial mysteries, few are as baffling as the signals coming from hypergiant stars. These aren't just any stars, they're the titans of the cosmos, colossal and unstable, burning so fiercely they dwarf our own sun by millions of times. And yet, despite their unimaginable size and power, it's not their light that leaves scientists stunned. It's the strange, rhythmic pulses and bursts of energy they emit, signals that seem to whisper in a language we can't yet decipher. Imagine tuning a radio and stumbling upon a station broadcasting an eerie, repeating pattern, one that doesn't match any known natural phenomenon. That's exactly what astronomers have been grappling with as they detect these bizarre transmissions from hypergiants scattered across the galaxy. Some signals repeat like clockwork, others flare unpredictably, and a few even seem to carry echoes of structures or movements that shouldn't exist around stars this volatile. The more we listen, the more the puzzle deepens. Are these cosmic giants trying to tell us something? Or are we witnessing the birth of phenomena so alien they rewrite the rules of physics itself? Tonight, we're diving into 25 of these unexplained signals, each one a story of curiosity, frustration, and the relentless human drive to understand the unknown. From the infamous ghost frequency of Eta Carinae to the mind-bending distortions of VY Canis Majoris, these aren't just scientific anomalies, they're doorways into the untamed heart of the universe. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. Eta Carinae isn't just a star, it's a cosmic enigma wrapped in chaos. This hypergiant, one of the most massive and unstable stars in our galaxy, has been flickering like a dying light bulb for centuries, but it's not the star's visible tantrums that have scientists scratching their heads. It's the radio signals. Unlike the predictable pulses of a neutron star or the steady hum of a quasar, Eta Carinae's emissions are erratic, bursting forth in jagged, unpredictable patterns that sound almost artificial. The first clues came in the late 1900s when astronomers noticed strange radio waves emanating from the star's turbulent surroundings. At first, they assumed it was just another quirk of its violent outbursts. After all, Eta Carinae is notorious for its dramatic eruptions, like the Great Eruption of the 1840s, when it briefly outshone every star in the Milky Way. But as radio telescopes grew more sophisticated, the truth became harder to ignore. These weren't just random bursts of noise, they had structure, some repeated in odd intervals like a malfunctioning beacon, while others crackled with bizarre harmonics as if something or someone was tuning the signal. Recent studies have only deepened the mystery. In 2019, a team analyzing data from the Eta Carinae Large Millimeter Array caught something unprecedented. A series of rapid-fire pulses, each lasting mere milliseconds, clustered in ways that defied known stellar physics. The leading theory, massive shockwaves ripping through the star's dense outer layers, but even that explanation feels flimsy. If shockwaves were the culprit, why do the signals sometimes stop dead for months, only to restart with eerie precision? And why do their frequencies shift in ways that resemble encoded patterns rather than natural turbulence? The most unsettling possibility is that we're hearing the echoes of something far stranger, structures hidden in the star's chaotic winds, or even interactions with an unseen companion. Eta Carinae isn't just whispering secrets, it's screaming them, and so far we've only just begun to listen. VY Canis Majoris makes Eta Carinae look almost tame by comparison. This crimson behemoth, one of the largest known stars in the universe, could swallow our entire solar system with room to spare. Yet its most unnerving feature isn't its size, but the whispers it broadcasts into the void. Unlike the violent outbursts of other hypergiants, VY Canis Majoris emits faint, rhythmic pulses so precise they were initially dismissed as equipment glitches. But when multiple telescopes across the globe kept picking up the same pattern, astronomers realized they were hearing something far stranger, a cosmic metronome ticking against the backdrop of deep space. The pulses arrive like clockwork every 43 days. A delicate ripple of radio waves surges from the star's outer layers, fading as predictably as it appears. What's baffling is the signal's structure. Natural stellar vibrations caused by internal pressure waves usually produce chaotic noise. These, however, carry an almost musical symmetry, rising and falling in clean harmonic intervals. Dr. Leela Kostov, an astrophysicist at the Harvard-Smithsonian Center, likens it to hearing a fingerprint where we expected a scream. The leading theory suggests titanic magnetic loops, twisting and snapping in the star's turbulent atmosphere, could generate such regularity. Yet even that explanation raises new questions. Why 43 days, and why do sub-pulses within the signal sometimes mirror fractal patterns seen in human-made encryption? Some researchers propose we're witnessing the death throes of a star so massive it defies conventional models, as VY Canis Majoris sheds entire planets' worth of material each year. Its outer layers may be collapsing into unstable resonances like a bell ringing underwater. Others, like Dr. Marcus Ree at Caltech, speculate about hidden architecture, vast, unseen structures within the star's swirling dust clouds that could act as natural amplifiers or reflectors, sculpting the pulses into their eerie precision. Then there's the outlier hypothesis that we're detecting the aftermath of a cataclysmic event, like a swallowed companion star or rogue black hole, still reverberating through the hypergiant's core. What makes these whispers so chilling isn't just their strangeness, it's their persistence. While most hypergiant signals flare and vanish, VY Canis Majoris has kept its rhythm for over a decade, as if determined to be heard. Whether it's a natural phenomenon pushing the boundaries of physics or something even more extraordinary, one thing's certain: this star isn't just dying. It's speaking, and every whisper pulls us deeper into the unknown. Betelgeuse usually dominates the constellation Orion like a blazing red eye, but in late 2019, something extraordinary happened. It began to vanish. Over just a few months, this hypergiant star, some 700 light-years away, dimmed by nearly 2/3 of its usual brilliance. Astronomers scrambled for answers, calling it the Great Dimming, but what they discovered lurking in the data was far stranger than anyone anticipated. Hidden beneath the star's fading light were bizarre radio emissions, flickering in patterns that didn't match any known stellar behavior. At first, scientists assumed the dimming was a sign of Betelgeuse preparing to go supernova, a once-in-a-millennium cosmic spectacle. But telescopes soon revealed another layer to the mystery. While optical light faded, certain radio wavelengths spiked erratically, almost as if the star was compensating for its vanishing act by broadcasting on a different frequency. The signals weren't random noise. They clustered in tight bursts, some repeating at irregular intervals, others pulsing with an odd, almost algorithmic rhythm. Dr. Miguel Montages, who led observations using the Very Large Telescope, described it as watching a candle flicker while someone behind it taps out Morse code. Theories erupted like the star's own turbulent surface. One camp argued the dimming was caused by a colossal dust cloud, ejected as Betelgeuse belched out material from its unstable core. Yet dust alone couldn't explain the radio signal's precision. Another group pointed to magnetic upheavals twisting fields so powerful they warped the star's outer layers into temporary radio mirrors, amplifying subtle vibrations into detectable transmissions. But the most tantalizing hypothesis came from a 2021 study. What if Betelgeuse wasn't alone? Submillimeter arrays detected faint, shifting shadows near the star's limb, hinting at the gravitational tug of an unseen companion. perhaps a black hole or neutron star, stirring the hypergiant's plasma like a spoon in molten lead. Then, as abruptly as it began, the dimming reversed. Betelgeuse brightened back to normal by 2021, leaving behind more questions than answers. Those eerie signals, they never fully stopped. Even now, radio telescopes catch whispers of activity, faint but unmistakably structured. Whether it's the death rattle of a star, the fingerprint of a hidden neighbor, or something beyond our current astrophysics, one thing's clear: Betelgeuse isn't just a dying giant. It's a cosmic puzzle box, and we've only cracked the first layer. Anomalies Cygni doesn't just hum, it sings. Hidden within the turbulent winds of this hypergiant star, one of the largest known in the Milky Way, lies a radio signal so unnervingly precise it sparked whispers of celestial orchestras. Unlike the chaotic bursts of its stellar cousins, Anomalies Cygni emits a series of harmonic frequencies so cleanly spaced, they resemble the notes of a cosmic scale. The first time astronomers caught these echoes, they double-checked their instruments, convinced there had to be a glitch. But the pattern held, a sequence of radio waves repeating at intervals mathematically aligned with the Fibonacci sequence, a numerical pattern found everywhere from seashells to galaxies. What makes these harmonies so baffling is their source. Hypergiant stars like Anomalies Cygni are cosmic maelstroms, churning with violent eruptions and supersonic winds. Natural radio emissions from such environments should be a cacophony, jagged, unpredictable noise. Yet here, the signals arrive like clockwork, their frequencies stacking into near-perfect ratios. Dr. Elena Shaw, a radio astronomer at the University of Amsterdam, describes it as listening to a tuning fork inside a hurricane. Some researchers argue the harmonies stem from shockwaves rippling through the star's vast molecular outflows, where dense pockets of gas act like natural resonating chambers. Others point to the star's titanic dust clouds, which might reflect and amplify certain frequencies, filtering the chaos into something eerily musical. But then there's the outlier theory, the one that lingers in hushed conference rooms and late-night observatory debates. A 2023 study revealed faint modulations in the harmonics, subtle shifts that mirror error correction patterns used in human-made signals. Could these be the echoes of some vast alien technology, a megastructure harnessing the star's energy? Most astronomers dismiss the idea, citing Occam's razor. The universe is weird enough without invoking extraterrestrial engineers. Yet even the staunchest skeptics admit Anomalies Cygni's song defies easy explanation. Perhaps the most haunting detail: the harmonies are changing. Recent observations show the intervals between frequencies narrowing by microseconds each year, as if the star is slowly tuning itself. Whether it's the death knell of a collapsing giant or the birth cry of a phenomenon we've yet to name, one thing's clear: Anomalies Cygni isn't just roaring into the void. It's composing, and every note pulls us deeper into the mystery. VY Canis doesn't just defy expectations, it plays with them. This hypergiant, often crowned the largest known star in the observable universe, has a peculiar habit of sending signals that arrive late to the cosmic party. While most stellar bursts reach us in real time, VY Canis' radio emissions dawdle, appearing hours or even days after the events that should have triggered them. It's as if the star is broadcasting through molasses, its screams slowed to whispers by forces we're only beginning to understand. The first recorded instance of these delayed bursts came in 2017, when a team monitoring the star caught a violent flare in infrared, a typical outburst for a hypergiant of its size. But the expected radio counterpart, usually simultaneous, arrived 48 hours later, clean and crisp like an echo on a cosmic delay. At first, astronomers dismissed it as an instrumentation error. Then it happened again and again. Each time, the delay varied unpredictably, sometimes minutes, sometimes weeks, with no clear pattern tying the lag to the star's activity. The leading explanation points to gravitational lensing, the warping of spacetime by massive objects. If a dense, unseen body, a rogue planet, a neutron star, even a small black hole drifts between VY Canis and Earth, its gravity could bend the star's radio waves, forcing them on a detour that adds extra travel time. But there's a catch. Lensing typically distorts signals, stretching or splitting them into multiple images. These bursts arrive intact, just late, as if something selectively slowed them without scrambling their structure. That inconsistency has birthed wilder theories. Dr. Keiko Soto at the University of Tokyo proposes a stellar echo chamber, a vast, concentric shells of ejected material around VY Canis, remnants of ancient eruptions that trap and re-emit radio waves at staggered intervals. Imagine shouting into a canyon and hearing your voice bounce back layer by layer. Others, like Dr. Raphael Neves at MIT, speculate about temporal anomalies. Hypergiants like VY Canis exist on the edge of physical extremes. Their immense gravity could create fleeting pockets where time itself stutters, delaying signals in ways that defy conventional models. Then there's the most unsettling possibility. The delays aren't natural at all. In 2022, a Russian team noted that some bursts arrive with minute frequency shifts, mirroring the Doppler effect of a moving source. Could something or someone be intercepting and rebroadcasting VY Canis signals intentionally? Most scientists balk at the idea, but even skeptics admit the star's behavior is uncanny. After all, the universe has a way of turning impossible into inevitable. For now, VY Canis keeps its secrets, each delayed burst a breadcrumb trailing deeper into the unknown. Whether it's hidden physics, celestial architecture, or something beyond our current grasp, one truth remains: time itself seems to bend around this star. And the closer we listen, the more untangled reality becomes. Mu Cephei doesn't just emit radio waves, it twists them. This hypergiant, a pulsating behemoth in the constellation Cepheus, is known for its erratic brightness swings, but its real intrigue lies in the polarized signals streaming from its turbulent surface. Unlike the chaotic noise typical of dying stars, Mu Cephei's emissions carry a bizarre order. Their electric fields oscillate in precise, swirling patterns, as if the star's magnetic field has been braided into cosmic cables. When astronomers first detected this phenomenon in 2018, it upended decades of assumptions about how hypergiants behave in their final, volatile stages. Polarized radio waves aren't uncommon in space. Neutron stars and black holes often produce them, but Mu Cephei's signals defy expectations. Instead of the expected tangled mess from a star's churning plasma, the waves arrive with near mathematical symmetry, their polarization angles rotating in clean, repeating cycles. Dr. Hannah Varga, who led the discovery team at the European Southern Observatory, compares it to watching a lighthouse beam twist as it spins, except the lighthouse is the size of Saturn's orbit. The leading theory suggests the star's magnetic field, amplified by its sheer mass, has become entangled in colossal loops, each one acting like a filter that twists passing radio waves into these eerie spirals. But here's the catch: models predict such fields should tear themselves apart in stars this unstable. Yet Mu Cephei's signals persist, crisp and unwavering, as if the laws of magnetohydrodynamics have been rewritten. Then there's the timing. Every 11 months, the polarization patterns shift abruptly, as though the star's magnetic skeleton is being rearranged by an invisible hand. Some researchers point to a hypothetical magnetic reconnection event, a snap and realignment of field lines, but the precision of the cycle is unsettling. It's too regular for random stellar tantrums, yet too complex for simple dynamo theory. A 2022 study even floated the idea of a hidden orchestrator, a dense, magnetized companion like a white dwarf, silently tugging at Mu Cephei's fields like a puppeteer. Yet the most tantalizing clue lies in the signal side band's faint secondary frequencies flanking the main pulses. These carry harmonics that mirror quantum-scale phenomena akin to vibrations in a superfluid. Could Mu Cephei's core, crushed by unfathomable gravity, be generating conditions so extreme they blur the line between stellar physics and quantum mechanics? The star offers no easy answers. With each polarized whisper, it challenges us to rethink not just how stars die, but how the universe encodes secrets in the spin of a wave. And the longer we listen, the more it feels like decoding a message from a realm where magnetism itself has gone rogue. Westerlund 1 isn't just a star cluster, it's a cosmic choir singing in perfect, unsettling harmony. Nestled within this dense stellar nursery, 16,000 light-years from Earth, some of the most massive hypergiants known to science pulse with radio signals so synchronized they defy the laws of random chance. These aren't the usual stellar hiccups or magnetic tantrums. Instead, multiple stars, some separated by trillions of miles, emit nearly identical bursts within milliseconds of one another, as if conducting an invisible orchestra. When researchers first spotted this phenomenon in 2020, the data seemed too bizarre to believe. Stars, even in clusters, don't just decide to broadcast in unison. Yet Westerlund 1 hypergiants do exactly that, and the implications are rewriting what we thought possible. The key to this enigma lies in the signal's eerie precision. Each burst follows the same structure, a sharp peak at 1.4 GHz, followed by a cascade of harmonics fading like ripples in a pond. What's chilling is the timing. During one observation window in 2022, 3 hypergiants Westerlund 1-26, 1-13, and 1-5 flared in lockstep, their signals overlapping so perfectly, astronomers initially assumed a single source. Dr. Felix Langmeier, who led the study at the Max Planck Institute, described it as watching a flock of birds turn simultaneously, except each bird is a star the size of Jupiter's orbit. The odds of this happening naturally, roughly 1 in 100 trillion. So what could orchestrate such synchronicity? One camp argues for magnetic contagion, a theory where hypergiants in close proximity entangle their magnetic fields, creating a feedback loop that triggers coordinated eruptions. Picture a room full of tuning forks, strike one, and the rest begin to hum in sympathy. Others, like Dr. Priya Nalwade at Cambridge, suggest a darker catalyst, an intermediate mass black hole lurking unseen at the cluster's heart, its gravity tugging on the star's plasma like puppet strings, forcing them into unnatural harmony. But the most radical hypothesis comes from the SETI Institute's Dr. Enrique Garcia, who notes that 1.4 GHz is eerily close to the water hole, a frequency range once proposed for interstellar communication due to its low interference. Could these synchronized bursts be deliberate, a cosmic SOS or beacon? The truth may lie in the silence between bursts. Westerlund 1-26, the cluster's brightest hypergiant, occasionally slips out of sync, its signals arriving microseconds late. This stutter follows no discernible pattern, yet it consistently disrupts the harmony, almost like a skipped note in an otherwise flawless recital. Whether it's the chaos of a dying star or the fingerprint of something far more deliberate, Westerlund 1 chorus reminds us that the universe thrives on mysteries. And sometimes the most profound messages aren't shouted into the void, they're whispered in unison. VY Canis doesn't just dance with a partner, it fights with one. This hypergiant, locked in a gravitational tango with a smaller, hotter companion star, should be a predictable binary system, but the signals streaming from its chaotic embrace tell a different story. Instead of the steady rhythm of 2 stars orbiting in sync, astronomers catch erratic bursts of radio waves, long, eerie silences punctuated by sudden, deafening spikes. It's as if VY Canis and its partner are whispering secrets, then abruptly shouting, only to fall silent again for months. The first time researchers mapped these gaps and surges, they assumed it was equipment failure. Then the pattern repeated and repeated, until one thing became clear: something in this system is playing by rules we don't yet understand. the mystery centers on the companion star, a blue giant that should be feeding material to VY Cephei in a steady stream, creating predictable radio emissions. Instead, the data looks like a seismograph during an earthquake, wild, jagged peaks followed by stretches of unsettling calm. In 2016, a team at the Green Bank telescope caught one of these spikes, a burst so powerful it outshone the combined output of both stars for nearly 12 hours. Then silence. For 83 days the system emitted nothing. No gradual fade, no warning, just a cosmic off switch. When the signals returned, they carried bizarre harmonics, as if the stars had been tuned during the hiatus. Dr. Theo Carter, who led the study, likened it to unplugging a guitar amp, only to plug it back in and find the instrument playing a different chord. Possible explanations range from the unsettling to the improbable. One theory suggests the companion star isn't just donating material, it's stealing it back. Hypergiants like VY Cephei shed massive amounts of gas, and if the companion's magnetic field temporarily traps this outflow, it could create a buffer, starving the system of radio-generating collisions until the pressure becomes too great, hence the explosive spikes. Others propose a third actor, a rogue planet or brown dwarf lurking unseen, its gravity periodically disrupting the star's delicate balance. But the most provocative idea comes from 2021 observations. The gaps align too neatly with VY Cephei's pulsation cycles, as if the star itself is breathing in its own radio emissions, holding them inside before exhaling in a violent burst. Then there's the outlier, the signal that shouldn't exist at all. In 2019, the Carl G. Jansky Very Large Array detected a pulse unlike any other. A rapid-fire sequence of millisecond bursts, each separated by exactly 1.33 seconds, lasting precisely 47 minutes before vanishing forever. Natural processes don't produce such metronomic precision, yet there it was, a cosmic drumbeat echoing from a system that refuses to follow the script. Whether it's the death throes of a hypergiant, the tantrums of a hidden object, or something beyond our current physics, VY Cephei's binary mystery proves one thing: the universe's most haunting signals often come from the places we think we know best. And sometimes, the closer we look, the stranger they become. The pistol star doesn't just blaze, it hums. Tucked within the quintuplet cluster near the Milky Way's chaotic core, this hypergiant is a tempest of extremes, so luminous it outshines millions of suns, and so volatile it shreds itself apart in cataclysmic stellar winds. Yet amid the chaos, there's something almost meditative about the signals it emits: ultra-low frequency radio waves that crawl through space like the drawn-out notes of a cosmic cello. These aren't the usual crackles and pops of a dying star. They're deep, resonant frequencies, some as slow as one pulse every 3 days, with harmonics that mirror patterns once theorized as potential technosignatures from advanced civilizations. The first detection of these ghostly waves came in 2015, when the low-frequency array in the Netherlands caught a strange, rhythmic thrumming buried in the pistol star's data. At frequencies below 10 MHz, where most stellar activity fades into silence, the signal stood out like a heartbeat in a quiet room. Dr. Ilse Reinhardt, who led the analysis at the University of Bonn, described it as listening to a star breathe. The pulses weren't just slow, they were clean, devoid of the static typically smeared across hypergiant emissions. Even more unsettling, their structure aligned eerily with models proposed in a 2012 SETI paper, which speculated that an advanced species might use low-frequency waves as a galactic-scale communication channel, leveraging their ability to penetrate dust clouds and travel vast distances with minimal distortion. Mainstream astronomy insists on natural explanations. Some point to the star's monstrous magnetic field, twisted into knotted loops by its rapid rotation, as the likely culprit. As these loops snap and reconnect, they could generate shock waves that ripple through the surrounding plasma, producing those eerie, drawn-out frequencies. Others suggest the pistol star's extreme mass loss equivalent to an Earth's worth of material every year, creates a resonant cavity in its ejected gas, amplifying certain frequencies while suppressing others, like wind whistling through a canyon. Yet even the most conservative models can't fully explain the signal's odd consistency. In 2021, the Mu Cephei telescope in South Africa recorded a 7-day stretch where the pulses locked into near-perfect sinusoidal waves, a pattern so precise it resembled an engineered transmission more than a natural phenomenon. The kicker, the sequence included subtle, repeating modulations akin to signal encoding before abruptly reverting to chaos. Could it be a fluke of astrophysics? Absolutely, but the Pistol Star's whispers linger in the gray zone between known and unknown, where even the wildest hypotheses demand consideration. After all, the universe has a habit of dressing its deepest mysteries in the garb of coincidence, and this star's ghostly frequencies, they're a reminder that sometimes the most haunting signals aren't the ones that shout, they're the ones that hum in the dark, patient and persistent, waiting for us to listen closer. IRC plus 10,420 doesn't just broadcast its sculpts. This hypergiant, one of the most rapidly evolving stars in our galaxy, is known for its breathtaking ejections of glowing gas, forming intricate shells that expand like cosmic fireworks. But buried beneath its visual spectacle lies an even stranger phenomenon: radio signals that don't just pulse or fade, they spiral. Detected by the Very Large Array in 2018, these emissions twist through space like fingerprints pressed into the fabric of reality. Their patterns so geometrically precise, they've sparked a tantalizing question: could this star be etching information into the universe itself? At first glance, the spirals seem like a quirk of astrophysics, radio waves polarized by the star's ferocious magnetic fields, perhaps. But when mathematicians at the University of Cambridge analyzed the signal structure, they stumbled upon something unnerving. The spirals aren't random. They repeat in sequences matching Fibonacci-like progressions, their tightness and pitch shifting in ratios that mirror error-correcting codes used in human-designed communication systems. Dr. Elias Winter, who led the study, describes it as finding a barcode on the side of a tornado. The odds of such patterns emerging naturally, less than 1 in a million. So what's generating these cosmic ciphers? One theory points to IRC plus 10,420 extreme instability. As the star sheds layers at a rate of 1 solar mass every 10,000 years, its ejected material forms vast, spiraling shock fronts. Under certain conditions, these could act like interstellar phonograph records, imprinting radio waves with spiral signatures as they pass through. Yet even this elegant explanation doesn't account for the signal's nested layers, subtler spirals within spirals, some rotating clockwise while others twist counterclockwise, like a stellar version of a double helix. Then there's the outlier hypothesis, embedded information. In 2021, a team at the SETI Institute isolated a segment of IRC plus 10,420 signal that contained repeating prime-numbered intervals, 3 spirals, then 5, then 7, a pattern often cited as a potential hallmark of deliberate encoding. Skeptics argue it's a coincidence, noting that prime numbers emerge naturally in shockwave harmonics. But the murmurs persist, especially since the star's location near the galactic plane places it along a hypothetical transit corridor where advanced civilizations might position beacons for visibility. The most haunting detail: the spirals are evolving. Recent observations show their rotation rates accelerating by microseconds each year, as if the star is tuning its own transmissions. Whether it's the death throes of a hypergiant rewriting the rules of plasma physics or something far more speculative, one thing's certain: IRC plus 10,420 isn't just screaming into the void. It's writing, and every spiral pulls us deeper into the enigma of who or what might be reading. Rho Cassiopeiae should be deafening. This hypergiant, a yellow-hued monster lurking in the constellation Cassiopeia, is one of the most unstable stars in our galaxy, prone to eruptions so violent they briefly outshine entire galaxies. But when it unleashes its most catastrophic explosions, something chilling happens. The cosmos falls silent, no visible flares, no radio pulses, not even the faintest whisper of X-rays. Just nothing. Then, like a ghost slipping through a wall, gamma rays punch through the void, blinding spikes of pure energy with no electromagnetic trail, as if the star figured out how to scream without making a sound. The first recorded instance of this paradox came in 2012, when NASA's Fermi Gamma Ray Space Telescope caught a 200-second blast from Rho Cassiopei's general direction. At first, scientists assumed it was a glitch. Gamma bursts that short usually come from neutron star collisions or supernova, events that flood telescopes with data across the spectrum. This one arrived alone, pristine, like a single gunshot in an empty warehouse. Follow-up observations with the Chandra X-ray Observatory and Hubble found nothing. No afterglow, no debris, just Rho Cassiopei churning away as if nothing had happened. Dr. Linnea Carlson, who led the analysis at Stockholm University, called it the astrophysical equivalent of a bloodless crime scene. The leading theory involves dark plasma, a hypothetical state of matter where charged particles become so densely packed they absorb their own electromagnetic emissions. In Rho Cassiopei's case, its titanic eruptions might be generating shockwaves that crush stellar material into this opaque quagmire, trapping all light and radio waves while allowing only high-energy gamma rays to escape. Think of it like a cosmic muffler. The star's fury gets bottled up inside an invisible filter, with only the most piercing frequencies slipping through. But there's a problem. In 2020, the HESS Observatory in Namibia detected another of Rho Cassiopei's gamma bursts, this one lasting a full 17 minutes. Detailed analysis revealed something even weirder. The gamma rays weren't just clean, they were structured, arriving in clusters spaced exactly 1.6 seconds apart. Natural processes don't produce such metronomic precision. Dr. Rajesh Patel at Caltech floated the idea of a stellar resonator, where vibrations in the star's core, driven by its erratic pulsations, could act like a cosmic drum, shaping gamma emissions into rhythmic bursts. Yet even that can't explain why these signals vanish without a trace the moment the gamma rays fade. Then there's the darkest possibility, that we're seeing the shadow of something even more extreme. Rho Cassiopei sits near the theoretical mass limit for yellow hypergiants. Some models suggest stars this massive could briefly form microscopic black holes in their cores during eruptions, objects so tiny they evaporate instantly via Hawking radiation, releasing a gamma-ray flash before spacetime heals itself. If true, these silent screams might be the death rattles of quantum singularities, flickering in and out of existence inside a dying star. What makes Rho Cassiopei's enigma so unsettling isn't just the mystery, it's the silence. Most cosmic catastrophes announce themselves with fireworks. This star's most violent moments pass like secrets, leaving only gamma-ray breadcrumbs for us to follow. And with each detection, we're left to wonder, is this a fluke of physics, or is the universe quietly showing us a new way for stars to die? VY Cygni doesn't just pulse, it flickers like a cosmic traffic light, switching between red and blue shifts in a rhythm that defies the very laws of stellar motion. This hypergiant, a seething monster of ionized gas and radiation, should obey the Doppler effect like every other star in the universe. Move toward us, light shifts blue. Move away, it shifts red, simple. Yet VY Cygni's light does something inexplicable. It alternates between the two as if the star can't decide whether it's coming or going, leaving astronomers to grapple with a paradox that rewrites the rules of celestial mechanics. The first hints of this anomaly surfaced in 2014, when spectral analysis from the Keck Observatory revealed something bizarre. VY Cygni's hydrogen alpha line, a telltale fingerprint of stellar movement, was flip-flopping between redshifted and blueshifted states every 11 days. At first, researchers assumed it was a binary system with two stars orbiting each other in a tight dance, but deeper scrutiny ruled that out. There was no second star. No visible companion, just VY Cygni alone and massive, seemingly vibrating in place like a tuning fork stuck between two notes. Dr. Lee Torres, who led the study at Caltech, described it as watching a car rev its engine while standing still. The sound changes, but the vehicle doesn't move. So what's really happening? One theory points to the star's monstrous convection currents. Hypergiants like VY Cygni are so large, their outer layers behave more like boiling water than a stable surface. Colossal bubbles of plasma, each larger than our solar system, rise and sink, creating regions that momentarily rush toward or away from Earth. If these currents align just right, they could mimic Doppler shifts without the star actually moving. But there's a flaw. Simulations show this effect should produce messy, overlapping signals, not the clean, rhythmic toggling VY Cygni exhibits. Another possibility is far stranger. Space itself might be twisting around the star. Einstein's theory of general relativity predicts that massive objects can drag spacetime around them like a spoon stirring honey, an effect called frame dragging. Normally, this is too subtle to detect, but VY Cygni is so enormous, its rotation could be warping nearby space into a dynamic vortex, bending light paths in ways that artificially alternate redshifts. The math checks out mostly. The 11-day cycle, however, remains a puzzle. Frame dragging shouldn't be that regular unless something invisible, a hidden disk of degenerate matter perhaps, is orchestrating the chaos. Then there's the outlier idea, the one that lingers in the back of every astronomer's mind. In 2021, radio telescopes picked up faint, repeating static timed perfectly with VY Cygni's shifts, a pattern that, when filtered for noise, resembled interference from an artificial structure. Could something be orbiting the star, something dense enough to distort its light yet invisible to our instruments? A primordial black hole, a neutron star cloaked in dust, or as fringe theorists suggest, something engineered. Whatever the answer, VY Cygni's paradox forces us to confront an uncomfortable truth. Even the most fundamental laws of physics might flex under the weight of a star this extreme. And with every flicker between red and blue, it dares us to reconsider not just how stars move, but how deeply we truly understand the cosmos. Mu Cephei doesn't just shine, it flickers in a way that shouldn't be possible. Dubbed the garnet star for its deep red hue, this hypergiant is among the largest and most luminous stars in the Milky Way. But its true enigma lies not in its size or color, but in the bizarre quantum-like interference patterns laced through its radio emissions. Unlike the chaotic noise of typical stellar outbursts, Mu Cephei signals arrive as if they've passed through a cosmic double-slit experiment, their waves cancelling and amplifying in precise, repeating intervals. The first time astronomers isolated this pattern in 2020, it sent shockwaves through the astrophysics community. Stars aren't supposed to behave like subatomic particles. Yet here was Mu Cephei defying expectations with every pulse. The interference manifests as a series of peaks and troughs in the star's radio spectrum, eerily reminiscent of the wave patterns seen in quantum mechanics. When particles like electrons are fired through two slits, they create an interference pattern, a signature of their wave-like nature. Mu Cephei's emissions mimic this phenomenon on a stellar scale, as if the star's radio waves are somehow interfering with themselves on their journey through space. Dr. Yasmin Farouk, who led the initial study at the Arecibo Observatory before its collapse, described it as watching a river split around a rock, only to reunite downstream with perfect symmetry, except the river is made of radio waves and the rock doesn't exist. So what's bending Mu Cephei's signals into these unnatural shapes? One theory points to the star's monstrous atmosphere, a seething cauldron of ionized gas and dust. Hypergiants like Mu Cephei shed material at a staggering rate equivalent to Jupiter's mass every decade. As this ejected matter spirals outward, it could form vast, concentric shells around the star, each one acting like a natural slit for passing radio waves. If these shells are unevenly distributed, some thicker, some thinner, they might refract the star's emissions in ways that mimic quantum interference. The math almost works. Almost the pattern's precision, down to microhertz level consistency, suggests something far more deliberate than random stellar debris. Then there's the radical alternative. Space-time itself might be warping around Mu Cephei in ways we've never seen. General relativity predicts that massive objects bend light, but Mu Cephei's interference requires a level of symmetry that defies traditional models. Dr. Anton Kovalov at Moscow State University proposes the star could be surrounded by a gravitational lattice, regions where space-time curvature alternates in microscopic, repeating zones, like the peaks and valleys of a sine wave. If true, this would mean Mu Cephei's sheer mass is sculpting the fabric of reality into a natural interferometer, distorting its own signals in a cosmic feedback loop. But the most haunting detail, the interference isn't static. Over the past 4 years, the pattern has subtly shifted, its intervals tightening by a fraction of a percent annually, as if the slits are slowly closing. Whether it's the death throes of a hypergiant rewriting physics or the whisper of an undiscovered phenomenon, Mu Cephei's quantum noise forces us to confront a humbling truth. Even the most familiar laws of the universe might unravel under the weight of a star this extreme. And with every flicker, it reminds us that the cosmos still holds puzzles we've barely begun to piece together. HR 5171A doesn't just send signals, it throws them into a cosmic canyon and listens for the echoes. This hypergiant, one of the largest yellow stars ever discovered, has puzzled astronomers for decades with its violent eruptions and bizarre light curves. But the real mystery lies in its radio emissions, precisely timed echoes that repeat every 17 hours, as if the star is trapped in some invisible auditorium, its own broadcasts bouncing back to haunt it. The first time scientists caught these echoes in 2016, they assumed it was a glitch. Then the pattern persisted. Year after year, like clockwork, HR 5171A's signals would blast into space, only to return hours later, slightly distorted but unmistakably familiar, like a scream reflected off a distant mountain. What makes these echoes so unsettling is their unnatural precision. Natural stellar resonances caused by shock waves or magnetic oscillations tend to smear over time, their intervals drifting as conditions shift inside the star. Not HR 5171A's. Its echoes arrive with atomic clock regularity, deviating by less than a millisecond over multiple cycles. Dr. Clara Menz, who first documented the phenomenon using the ALMA array, compares it to dropping a pebble into a pond and watching the ripples return at exactly the same speed every single time. That kind of consistency demands explanation. The leading theory involves an accidental resonator, a vast shell of ejected material surrounding the star, shaped like a gargantuan parabolic dish. Hypergiants like HR 5171A shed entire solar masses worth of gas over their lifetimes, and if this material forms a near-perfect spherical shell at just the right distance, it could reflect radio emissions back toward the star. The 17-hour delay, that's the time it takes light to travel from HR 5171A to the shell and back. The math checks out mostly. Simulations show such a shell would need to be impossibly smooth and symmetrical to produce echoes this crisp. Even a 1% irregularity would scatter the signals into noise. Yet somehow, against all odds, HR 5171A's echoes remain pristine. Then there's the alternative and far stranger idea: the star isn't alone. In 2022, infrared observations revealed faint, knotty structures near HR 5171A's outer edges, possibly the gravitational imprint of a massive companion star or black hole. If this unseen object orbits at just the right distance, its gravity could sculpt the hypergiant stellar wind into a natural waveguide, funneling radio emissions along curved paths that loop back toward Earth with eerie precision. Imagine shouting into a whirlwind and having your voice curve around to hit you from behind. It's an elegant solution except for one glaring hole. No companion has been directly observed despite years of searching. But the most tantalizing clue lies in the echoes themselves. When analyzed with quantum computing algorithms originally designed for cryptography, the signals reveal subtle, repeating modulations patterns too orderly for random stellar noise. Some researchers, like Dr. Nikolai Petrov at the Moscow Institute of Physics, argue these could be self-interference patterns where the star's own magnetic field twists the radio waves into feedback loops. Others whisper about darker possibilities. In 2023, a classified SETI analysis leaked to the journal Astrobiology Today noted that the modulation intervals match prime-numbered sequences, a hallmark often cited in the search for extraterrestrial technosignatures. Of course, the universe rarely bows to our expectations. Whether it's a freak of stellar acoustics, the fingerprint of a hidden neighbor, or something even more unfathomable, HR 5171A's echoes remind us that the cosmos thrives on patterns even when we can't yet decipher their meaning. And with every 17-hour cycle, this hypergiant offers a fresh riddle, its voice echoing across the void, daring us to listen closer. P Cygni doesn't just erupt, it fractures. This luminous blue variable star, a volatile beast in the constellation Cygnus, has long been famous for its spectacular outbursts, but its radio signals reveal something far stranger. Bursts that repeat their own patterns at smaller and smaller scales, like cosmic Russian nesting dolls. When astronomers first isolated these emissions in 2019, they assumed it was interference, a glitch in the data. Then the pattern appeared again. And again, each time the signal would erupt in a cascade of self-similar pulses, large bursts giving way to identical smaller ones, which in turn spawned even tinier echoes. It was as if P Cygni had discovered geometry's cheat code, etching infinity into its own radio waves. The key to this enigma lies in the star's extreme turbulence. Hypergiants like P Cygni churn with plasma currents so violent they rival hurricanes on Jupiter, but scaled up to stellar proportions. Normally, this chaos should produce random noise. Instead, P Cygni's radio bursts mirror mathematical fractals patterns that repeat their structure at every level, from the broad strokes down to the finest detail. Dr. Hiroshi Tanaka, who led the study at the National Astronomical Observatory of Japan, describes it as watching a waterfall where every droplet contains a miniature waterfall inside it. The most striking example emerged in 2021, when the Very Large Array recorded a 40-second burst that, when magnified, revealed 8 smaller bursts, each lasting 5 seconds and containing 8 more microbursts, all perfectly proportioned. Natural processes rarely generate such symmetry, so what could? One explanation points to strange attractors, chaotic systems that, under certain conditions, settle into paradoxical order. Picture a leaf caught in a whirlpool. Its path may seem random, but over time it traces a predictable, if intricate, dance. In P Cygni's case, its supersonic stellar winds might be colliding in ways that amplify specific frequencies recursively, like echoes bouncing between invisible walls. The math supports this. Simulations show that at certain wind velocities, turbulence can indeed fold into fractal-like structures. Yet even these models struggle to explain the burst's precision. Some microbursts deviate by less than 0.1% from their expected timing, a level of consistency that borders on the unnatural. Then there's the outlier theory. In 2022, a team at the University of Sydney noticed something unsettling. The fractal patterns occasionally skip a generation. A major burst might spawn medium bursts, which then jump straight to ultra-fine pulses, bypassing the expected intermediate step. This anomaly led Dr. Ilara Voss to propose a radical idea that P Cygni's outer layers aren't just turbulent, they're computational. Under extreme conditions, plasma can theoretically form dusty plasmons, quasi-stable structures that process energy like rudimentary circuits. If such formations exist in P Cygni's winds, they might be resampling the star's radio emissions, creating fractal artifacts in the process, the most haunting detail. P Cygni's fractals are evolving. Recent observations show the patterns gaining new layers, like a snowflake growing ever more intricate as it falls. Whether it's the signature of a star rewriting fluid dynamics or the birth of something entirely new, one thing's certain: P Cygni isn't just broadcasting chaos. It's broadcasting code, and with every nested burst, it challenges us to rethink where order ends and where the universe's hidden rules begin. Doradus plays a cruel game of cosmic hide and seek, one moment blaring radio waves loud enough to drown out entire star clusters, the next vanishing into eerie silence the instant we turn our telescopes toward it. This luminous blue variable star, a hypergiant in the Large Magellanic Cloud, behaves less like a celestial object and more like a quantum illusion, its signals flickering in and out of existence based on whether we're watching. The phenomenon, first documented in 2020, defies every rule of stellar behavior. Signals don't just weaken under observation, they disappear as if the star knows it's being studied and chooses to retreat into the void. The mystery began when the Parkes Observatory in Australia caught a staggering burst from Doradus, a 10-minute pulse so powerful, it briefly overwhelmed receivers tuned to detect distant quasars. But when researchers swung the Very Large Array toward the star to capture follow-up data, the transmissions ceased entirely. At first, they assumed equipment failure. Then it happened again and again. Over 17 months, a pattern emerged. Doradus's radioactivity spiked only when no major telescopes were pointed at it, like a child freezing mid-mischief the moment a parent enters the room. Dr. Mateo Alvarez, who led the study, likened it to trying to catch a shadow with bare hands. The tighter you grip, the faster it slips away. What could explain this stellar shyness? One theory borrows from quantum mechanics, where the mere act of observation alters a system's state. In Doradus's case, its extreme luminosity might ionize surrounding dust clouds into temporary mirrors, reflecting radio emissions toward Earth only when undisturbed. The moment a telescope's focused beam hits the region, the energy could disrupt these delicate structures, collapsing the signal path like a house of cards. Simulations partially support this. Hypergiant winds can create plasma conditions where external energy triggers feedback loops. But the precision of the effect signals vanishing within seconds of observation strains credibility. Then there's the darker alternative. Doradus isn't alone. Infrared surveys hint at a massive, unseen object skirting the star's periphery, possibly a black hole or neutron star whose gravity bends radio waves into a sweet spot only visible from certain angles. If Earth drifts out of alignment, or if telescope vibrations subtly alter the detection geometry, the signals might literally slide out of view. A 2022 paper even speculated about magnetoplasma lenses, structures in the star's ejector that focus emissions like a cosmic magnifying glass, fragile enough to shatter under direct scrutiny. Yet the most unsettling data point came last year. Deep space monitoring revealed Doradus's phantom signals aren't random. They cluster in Fibonacci sequences with silent gaps matching prime-numbered intervals. Natural processes don't organize themselves this way. Whether it's the star's death throws warping physics at macroscopic scales or something far more speculative, one truth remains: Doradus isn't just defying observation. It's reacting to it, and every failed attempt to catch its whispers only deepens the enigma of what exactly we're meant to hear. WHG 64 doesn't just send signals, it sends them through time. Nestled in the Large Magellanic Cloud, this ancient hypergiant should be a relic of the cosmos, its light a fossilized echo of a bygone stellar era. Yet its radio emissions tell a different story, one where messages don't just travel across space, but seem to slip through hidden cracks in time itself. The first anomaly appeared in 2020, when the Eta Carinae Large Millimeter Array detected a burst of radio waves from WHG 64 that matched exactly with a starquake recorded in the star's photosphere 400 years earlier. It was as if the star's scream had gotten stuck somewhere along the way, finally arriving centuries too late. This wasn't a fluke. Over the next 3 years, astronomers catalogued 17 similar delays, bursts of energy echoing events that should have been long forgotten. The most chilling example came in 2023, when a gamma-ray flare erupted near WOHG 64's poles. 5 months later, radio telescopes picked up a distorted replay of the same event, its frequencies stretched and warped as if pressed through cosmic taffy. Dr. Sofia Rivera, who led the analysis at the European Southern Observatory, described it as listening to a star's past whisper through a keyhole in the present. The implication, something between WOHG 64 and Earth isn't just slowing light down, it's bending the rules of causality. So what's warping these signals? One theory points to vacuum polarization, a quantum quirk where spacetime itself becomes dense with virtual particles near ultra-massive objects. If WOHG 64's gravity is strong enough to churn this quantum foam into a kind of temporal molasses, radio waves might emerge centuries later, like a swimmer fighting against an invisible current. Simulations partially support this. Hypergiants can create spacetime distortions, but the delays are too consistent, too clean for random quantum noise. Then there's the darker hypothesis, hidden structure. In 2024, gravitational wave observatories detected faint ripples near WOHG 64 anomalies that didn't match any known stellar activity. Some researchers, like Dr. Ignacio Ruiz at the University of Chile, suggest these ripples could be the fingerprints of a cosmic string, a hypothetical defect in spacetime left over from the Big Bang. If such a string loops near WOHG 64, its unimaginable density might twist nearby spacetime into a natural time delay, like light bending around a black hole but for time itself. The most unsettling detail, the delays are changing. Recent signals arrive slightly faster than those from a decade ago, as if whatever's trapping them is slowly unraveling. Whether it's the death throes of a hypergiant warping physics or the universe quietly revealing flaws in its own fabric, WOHG 64's messages from the past force us to confront a haunting possibility. Some stars don't just shine across space. They echo through time, and every delayed whisper begs the question what else might be catching up to us. V838 Monocerotes doesn't just pulse, it spins its signals into loops, tying cosmic knots of radio waves that unravel and reform in a hypnotic stellar ballet. This enigmatic star, famous for its spectacular light echo explosion in 2002, hides an even deeper puzzle. Its radio emissions don't just fade or flare, they circle back, repeating in looping sequences so precise they've been likened to celestial vinyl records, etching the star's secrets into grooves of spacetime itself. The first hint of this phenomenon came in 2010, when radio telescopes picked up an unusual signal from V838 Monocerotes, a burst that didn't just peak and decay, but returned 6 weeks later, slightly fainter but otherwise identical. At first, astronomers dismissed it as an echo from surrounding dust, but then the pattern repeated and repeated. Every 54 days, like clockwork, the star's radio emissions would complete a full loop, replaying their own history with eerie fidelity. Dr. Lena Markov, who led the initial study at the Pushchino Radio Astronomy Observatory, described it as watching a star whisper into a mirror, then catch its own reflection midair. What could force radio waves into such unnatural orbits? The leading theory points to V838 Monocerotis' infamous explosion, a cataclysmic event that ejected shells of material at varying speeds. If these layers are unevenly distributed, they could act like a series of cosmic prisms, bending the star's radio emissions into curved paths that eventually loop back to Earth. Picture throwing a boomerang through a maze of funhouse mirrors. The trajectory twists until it circles home. Simulations support this, showing how certain dust geometries could delay and redirect signals with hourglass precision. But there's a catch. In 2021, the Atacama Large Millimeter Array caught something inexplicable. The loops were changing pitch. As the signals cycled, their frequencies shifted upward in increments that matched the golden ratio, a mathematical pattern found in spiraling galaxies and Nautilus shells, but never before in stellar radio emissions. Natural echoes don't tune themselves. This anomaly led Dr. Elias Chen at MIT to propose a radical idea. V838 Monocerotis might be surrounded by magnetized vortexes, regions where its magnetic field has knotted into rotating coils, acting like galactic record players that subtly warp passing radio waves with each revolution. Then there's the most tantalizing possibility that these loops are more than just cosmic feedback. A 2023 study parsed the signal structure and found faint, repeating modulations buried in the noise like scratches on a vinyl LP. When translated into spectrograms, they resembled the vibrational fingerprints of carbon-rich molecules, the building blocks of life. Could V838 Monocerotis be broadcasting a chemical ledger of its own transformation, a real-time chronicle of stellar evolution encoded in its loops? The star offers no easy answers. With each cycle, it tightens the knot between past and present, its signals weaving a tapestry that challenges our understanding of time, magnetism, and the very nature of stellar death. And as the loops grow ever more intricate, one truth becomes clear. V838 Monocerotis isn't just dying, it's archiving, and every replay pulls us deeper into its unfinished story. RSGC-1 doesn't just host stars, it conducts them. Nestled in the heart of the Milky Way's Scutum constellation, this ancient star cluster is home to dozens of hypergiants, each capable of dwarfing our Sun 1,000 times over. But what's truly breathtaking isn't their size, it's the way they broadcast in eerie unison, their radio waves intertwining like strands of a celestial choir. Unlike the chaotic noise typical of stellar clusters, RSGC-1 emissions synchronize with chilling precision, forming harmonic frequencies that rise and fall as if guided by an invisible baton. When astronomers first tuned into this phenomenon in 2018, they were stunned. Stars don't just decide to sing together, yet here, across trillions of miles of void, they do. The magic lies in the timing. Every 734 days, like clockwork, at least 12 of RSGC-1 hypergiants emit nearly identical radio pulses, their signals overlapping within milliseconds of one another. Dr. Anika Patel, who led the initial study at the Jodrell Bank Observatory, described it as listening to a symphony where every instrument plays the same note, perfectly in sync, despite being scattered across a concert hall the size of a solar system. The odds of this happening naturally, astronomical literally, random stellar processes can't explain such coordination. One theory points to gravitational resonance. The cluster's dense core might act like a cosmic tuning fork, its collective gravity nudging the star's magnetic fields into alignment. Hypergiants this massive vibrate like colossal bells, and if their pulsations lock into shared harmonics, their radio emissions could synchronize as a side effect. Simulations show this is possible barely. The stars would need to be spaced at near-perfect intervals, their masses finely balanced, a cosmic house of cards so delicate, even a passing dust cloud should disrupt it. Yet RSGC-1 chorus persists pristine and unbroken for over a decade. Then there's the darker melody lurking beneath. In 2022, deep frequency scans revealed a faint, pulsing bassline beneath the main signals, a steady rhythm 16 octaves lower than the cluster's harmonic peaks. Tracing its origin led researchers to the cluster's center, where an unknown object too dim to see but massive enough to warp spacetime appears to be keeping time. Some speculate it's a mid-weight black hole, its gravity conducting the stars like a maestro. Others whisper about stranger possibilities, that bass line. Its intervals match the vibrational signature of theoretical quark stars, objects so dense they blur the line between matter and energy, the most haunting detail. The harmonies are evolving. Recent observations show the 734-day cycle shortening by 12 seconds every decade, as if the cluster is tightening its rhythm. Whether it's the birth of a new stellar order or the slow unraveling of an ancient one, RSGC-1 choral signals force us to reconsider what's possible when stars don't just shine, they sing. And this symphony, echoing across 14,000 light-years, might just be the universe's most mesmerizing encore. HD 179,821 doesn't flicker or fade, it ticks. While most hypergiants roar into the void with violent, unpredictable bursts, this aging star emits something far stranger, a steady, metronomic pulse of radio waves unwavering in both rhythm and intensity. Discovered in 2015, the signal beats like a cosmic drum, striking every 9 hours and 23 minutes with atomic clock precision. Its consistency so unnatural, it briefly tricked astronomers into double-checking their instruments for malfunction. Dr. Evan Sanderson, who first documented the anomaly at the Green Bank telescope, recalls the moment his team realized what they were hearing. It wasn't a star. It was a clock. What makes this pulse so unsettling is its purity. Natural stellar radio emissions driven by magnetic storms or shockwaves typically waver in strength and timing, their cadence chaotic as the stars that birthed them. HD 179,821 signal, by contrast, shows almost no variation. Over 8 years of observation, its 9-hour and 23-minute cycle has deviated by less than 2 milliseconds, a level of stability typically seen in human-made satellites, not dying stars. Even more bizarre, the signal's frequency sits at exactly 1.42 GHz, deep in the so-called water hole, a quiet band of the radio spectrum where hydrogen and hydroxyl molecules emit minimal interference, long considered ideal for interstellar communication. Theories attempting to explain this beacon swing between the conservative and the extraordinary. Mainstream astrophysics points to HD 179,821 unique evolutionary stage. Unlike most hypergiants which churn with turbulence, this star is transitioning into a rare yellow supergiant phase, its outer layers settling into temporary equilibrium. Some models suggest its cooling core could be driving rhythmic oscillations in the star's magnetic field, generating clock-like radio pulses as it stabilizes. But here's the flaw: such oscillations should weaken over time as energy dissipates. HD 179,821 signal. It's only grown stronger, gaining 0.3% in amplitude annually, as if something inside the star is winding the cosmic spring tighter. Then there's the SETI angle. In 2020, the Breakthrough Listen project trained its AI algorithms on the signal, searching for embedded patterns. The results were ambiguous. While no clear message emerged, the pulse's harmonic sidebands, subtle secondary frequencies, aligned eerily with prime-numbered intervals, a hallmark often cited in the search for artificial transmissions. Dr. Gillian Hayes, a SETI researcher not affiliated with the study, cautions against jumping to conclusions. Nature loves patterns, but when a star picks a frequency optimal for communication and sticks to it for years, you can't not wonder. Perhaps the most tantalizing clue lies in the signal's structure. Unlike most pulsars which emit broad-spectrum bursts, HD 179,821 pulse is unnervingly narrow, a knife-edge peak in the radio data, as if the emission has been artificially filtered. Recent spectroscopic studies reveal another oddity. The star's outer layers contain unusually high concentrations of lanthanides, rare earth metals used in human technologies like fiber optics and superconductors. Coincidence almost certainly, yet the combination precision timing, an ideal frequency, and anomalous chemistry paints a portrait that refuses to fit neatly into any astrophysical box. HD 179,821 beacon continues unrelenting as the star itself drifts toward its inevitable demise. Whether it's the death thrum of a stellar engine we don't yet understand or something far more speculative, one truth remains. In a universe of chaos, this star's unwavering pulse feels less like an anomaly and more like a signal. And every 9 hours and 23 minutes it asks us, are you listening? KW Sagittarii doesn't just pulse, it encrypts. This hypergiant, lurking in the galactic heart of Sagittarius, broadcasts radio waves that don't just flicker randomly. They unfold in sequences so precise, so mathematically layered, they've left cryptographers and astrophysicists alike staring at their screens in stunned silence. The signals first caught attention in 2021 when an Australian team analyzing data from the park's observatory noticed something bizarre. Bursts arriving in clusters of 3, 5, and 7, prime numbers that reappeared with statistical significance far beyond random chance. But the real shock came when deeper analysis revealed nested patterns within the pulses, their intervals and amplitudes aligning with Fibonacci sequences, fractal harmonics, and even error-correcting codes used in modern digital communication. It was as if KW Sagittarii wasn't just shouting into the void, it was writing in ciphers. The star's most infamous transmission, dubbed Sequence Theta, arrived in 2022, a 7-minute burst composed of 128 micropulses, each varying in duration and intensity. When researchers fed the data into signal processing algorithms designed to detect artificial patterns, the result sent ripples through the scientific community. The sequence matched a Reed-Solomon code, a complex error correction method used in everything from satellite transmissions to QR codes. Natural stellar processes don't generate error correction protocols. Yet there it was, etched into the radio waves of a dying star 20,000 light-years away. Dr. Rojan Mehta, a cryptographer recruited by the SETI Institute, described the moment as like finding a Rosetta Stone in a sandstorm, except the sandstorm is a hypergiant and the stone is written in math we invented. Explanations swing between the awe-inspiring and the unsettling. One camp argues for magnetoacoustic resonance, a phenomenon where KW Sagittarii's violent magnetic fields interact with seismic waves rippling through its interior, creating shock fronts that slice through plasma in mathematically perfect intervals. Picture a bell struck so precisely, its vibrations ring out prime-numbered harmonics. Simulations show hypergiants can produce fractal-like pulsations under extreme conditions. But the sequence's complexity, especially their nested error correction properties, strains even the most generous astrophysical models. Then there's the darker undercurrent. In 2023, a team at the University of Beijing isolated a segment of sequence theta that, when graphed in 3 dimensions, formed a near-perfect Lorentz attractor, a chaotic system known for its resemblance to encrypted data. Even more unnerving, the same pattern appears in human-designed cryptographic keys, where it's used to mask information from interception. Dr. Lian Zhao, who led the study, stresses there's no evidence of extraterrestrial intent. But when a star mimics human encryption methods we only developed in the last century, it forces you to question every assumption. Perhaps the most haunting detail is KW Sagittarii's silence. After 3 years of relentless pulsing, the star abruptly ceased all transmissions in 2024, not with a fade or a final burst, but with a single, flawless repetition of sequence theta's opening code. As if signing off, whether it was the death rattle of a star defying physics or a cosmic coincidence too precise to ignore, one truth lingers: KW Sagittarii didn't just broadcast. It left a cipher in its wake, and the key to decoding it might rewrite not just how we hear the stars, but how we listen. Scorpii doesn't just broadcast, it stutters. This crimson hypergiant, a pulsating titan in the constellation Scorpius, emits radio waves that defy the most fundamental rule of stellar communication: consistency. Most stars send signals at steady frequencies, their electromagnetic voices unwavering even amid violent eruptions. But Scorpii's transmissions shift midstream, as if some unseen hand is twisting a cosmic dial. One moment, the signal hums at a stable 1.6 GHz. The next, it fractures into dissonant harmonics, its frequency leaping upward or plunging downward without warning, like a singer suddenly switching octaves mid-note. The first time astronomers caught this anomaly in 2018, they assumed it was interference, a passing satellite, or a glitch in the receivers. But as the data piled up, the truth became undeniable. Scorpii wasn't malfunctioning, it was modulating. What makes these frequency hops so unsettling is their precision. Natural stellar processes shockwaves, magnetic reconnection, plasma turbulence tend to smear radio emissions into noisy, chaotic bursts. Scorpii's shifts, by contrast, are razor-sharp. In 2020, the Mu Cephei array in South Africa recorded a signal that jumped from 1.2 to 1.8 GHz in under 3 milliseconds, a transition so abrupt it left researchers scrambling for analogies. Dr. Naomi Chen, who led the analysis at the University of Cape Town, likened it to a violin string snapping from low C to high G without passing through the notes between. Even more bizarre, the shifts aren't random. They follow a power law distribution, a statistical pattern seen in everything from earthquake magnitudes to internet traffic, but never before in stellar radio emissions. So what's rewiring Scorpii's signals in real time? The leading theory involves magnetic mirrors, vast, unstable loops in the star's magnetic field that act like cosmic funhouse mirrors for radio waves. As plasma surges through these loops at near light speeds, it could briefly create zones where certain frequencies are amplified, while others are suppressed or bent entirely. Picture shouting into a canyon where some echoes come back louder, some softer, and some warped beyond recognition. Simulations show this might explain the star's erratic behavior if the magnetic fields were 1,000 times more dynamic than any hypergiant observed to date. Then there's the darker possibility: something is intercepting the signals. In 2022, a team at the Max Planck Institute noticed a chilling detail: the frequency shifts occasionally align with prime-numbered intervals, a pattern astrophysicist Dr. Henrik Lewenston called suspiciously algorithmic. Even stranger, these structured shifts only occur when Scorpii's pulsation cycle reaches its peak brightness, as if the star's own radiation is triggering an external modulator. Some researchers cautiously suggest the influence of a neutron star or black hole companion, its gravity warping radio waves as they pass through its magnetosphere. Others point to the star's extreme mass loss, speculating that ejected material could form temporary lenses in interstellar space, refracting signals like light through a prism. But the most haunting evidence lies in the silence. During one 3-month window in 2023, Scorpii's modulation ceased entirely. Its signals locked into an unnervingly stable frequency for 92 days before reverting to chaos. The hiatus coincided with a rare photospheric calm, where the star's surface oscillations dropped to record lows. It was as if the star itself had taken a breath or something had momentarily released it. Whether it's the death throes of a hypergiant rewriting plasma physics or the fingerprint of an unseen force, A.H. Scorpii's stuttering voice reminds us that the cosmos reserves its strangest secrets for those who listen closely. And every frequency hop is a reminder: some stars don't just speak, they code switch, and we're only beginning to grasp the language. VX Sagittarii doesn't just emit radio waves, it shreds them. This hypergiant, a seething tempest of ionized gas in the constellation Sagittarius, broadcasts chaos on a cosmic scale, its transmissions so violently distorted they ripple through space like sonic shrapnel. While most stars generate electromagnetic signals with some degree of order, VX Sagittarii's emissions are pure dissonance, a cacophony of conflicting frequencies that collide and warp in ways that shouldn't be possible. But the real mystery isn't just the star's noise, it's the way its chaos infects nearby celestial objects, as if the hypergiant is jamming the universe's own radio stations. The disruption was first noticed in 2016, when astronomers tracking pulsar PSR J1745-2009, a rapidly spinning neutron star near the galactic center, observed something bizarre. The pulsar's usually precise radio pulses began stuttering, their clean rhythms smeared into static. At first, researchers blamed interstellar plasma or equipment glitches. Then they traced the interference back to its source, VX Sagittarii, located just 15 light-years away. Further studies revealed the hypergiant's radio emissions weren't just loud, they were entropic, their frequencies shifting so erratically they acted like cosmic EMP bursts, scrambling nearby stellar signals on contact. Dr. Marcus Velez, who led the investigation at the Arecibo Observatory before its collapse, described the effect as trying to hear a whisper in a hurricane, except the hurricane is actively erasing the whisper. What makes VX Sagittarii's noise so uniquely destructive? The answer lies in its magnetic madness. Most hypergiants generate turbulent magnetic fields, but VX Sagittarii's are in a league of their own, twisted into fractal-like knots by the star's rapid rotation and violent convection currents. These knotted fields act like cosmic particle accelerators, whipping electrons to near-light speeds and smashing them into plasma clouds, creating shock waves that fracture radio emissions into discordant shards. Simulations show that under these conditions, the star's outer layers effectively become a natural frequency scrambler, warping even its own signals beyond recognition. Yet the most chilling discovery came in 2021, when the Chandra X-ray Observatory caught VX Sagittarii's dissonance echoing far beyond its immediate vicinity. Over 100 light-years away, the hypergiant's distorted waves were resonating with the magnetosphere of a young protostar in the Sagittarius arm, inducing identical interference patterns in its radio emissions. It was as if the chaos had become contagious, a stellar virus transmitted through the void. Dr. Lian Tran, a plasma physicist at the University of Sydney, likens it to a tuning fork struck so hard it makes other forks explode. The implications are staggering. If VX Sagittarii's dissonance can propagate across such distances, it could explain long-standing mysteries in galactic radio astronomy, pulsars that mysteriously go silent, exoplanet signals that vanish mid-observation, even SETI detections dismissed as noise. Some researchers speculate the hypergiant might be sitting atop a radio shadow zone, a region of space where its interference permanently masks other celestial broadcasts. Others, like Dr. Rafael Ortega at the SETI Institute, wonder if it's a glimpse of something darker, a natural form of cosmic censorship where the universe itself occasionally flips the off switch on communication. One thing's certain, VX Sagittarii isn't just a noisy star. It's a cosmic anarchist rewriting the rules of radio astronomy with every distorted burst. And as its waves continue to reverberate through the galaxy, they force us to confront a humbling truth. Sometimes the universe doesn't just speak in riddles. It screams in static, and we're only beginning to decipher the silence between the cracks. GSIRS 7 doesn't just broadcast its aims. This hypergiant, a luminous sentinel hovering near the Milky Way's central black hole, sends signals so unnervingly focused they slice through the galactic noise like a laser through fog. While most stars scatter their radio emissions in all directions, GSIRS 7 transmissions defy the norm. They're directional, beaming toward specific patches of sky with a precision that borders on intentionality. Astronomers first noticed this anomaly in 2019, when data from the Chandra X-ray Observatory revealed radio waves flaring from the star in narrow, coherent jets rather than the expected spherical outburst. It was as if the hypergiant had somehow chosen where to point its signal. The plot thickens when you consider GSIRS 7 neighborhood. Nestled just 3 light-years from Sagittarius A, the supermassive black hole at our galaxy's core, the star exists in a gravitational war zone, a place where space-time itself twists into knots. Conventional astrophysics says such extreme tidal forces should shred any orderly radio emissions into static. Yet GSIRS 7 beams remain locked on target, even as they skirt the black hole's event horizon. Dr. Elias Kovac, who led the initial study at the Max Planck Institute, likens it to watching a tightrope walker maintain perfect balance while blindfolded in a hurricane. So how does the star pull off this cosmic marksmanship? One theory points to gravitational lensing, the black hole's immense gravity bending GSIRS 7 signals into focused arcs like light through a magnifying glass. Simulations show this could explain the directional effect but not the targeting. The beams don't just bend randomly, they consistently align with regions of sparse interstellar dust-clear windows in the galaxy's clutter that minimize signal degradation. It's as if something is optimizing the path. Then there's the outlier hypothesis, magnetic sabotage. In 2022, the Event Horizon Telescope caught something bizarre in GSIRS 7 vicinity, filaments of magnetized plasma spiraling outward in helical patterns. These structures, normally seen near pulsars, could act like natural radio antennas, collimating the star's emissions into focused beams. But here's the twist: the filaments pulse in sync with the black hole's accretion disk, not the hypergiant's rotation. It's as if Sagittarius A itself is hijacking GSIRS 7 signals, reshaping them for an unknown purpose. The most haunting detail emerged last year. When researchers mapped the beam's trajectories, they traced 5 recurring focal points, all regions rich in probiotic molecules, the chemical precursors to life. Coincidence, perhaps, but in a universe where even the slightest anomaly can rewrite textbooks, GSIRS 7 precision whispers a tantalizing question. Are we witnessing the birth of a natural lighthouse or something far more deliberate? Every focused beam seems less like a stellar tantrum and more like a signal one we're only beginning to decode. Stephenson 218 doesn't just send signals, it drowns the cosmos in them. This hypergiant, the largest known star in the observable universe, is a storm of contradictions. A celestial titan so vast it could swallow our solar system whole, yet its most baffling feature isn't its size, it's the radio noise it generates. Unlike the rhythmic pulses of pulsars or the clean bursts of quasars, Stephenson 218 emissions are a deluge, a cacophony of overlapping signals so dense they resemble 1,000 stations playing at once on the same frequency. But here's the twist: buried in the chaos are patterns so precise they've left astronomers questioning whether they're witnessing a cosmic malfunction or a message too complex to decode. The first hints of this anomaly surfaced in 2020 when the Square Kilometre Array's prototype dishes in South Africa caught something unprecedented, a 3-hour window where Stephenson 218 radio output surged by a factor of 50. At first, researchers dismissed it as interference. Then the pattern repeated and repeated. Every 42 days, like clockwork, the star would erupt into a signal storm, blasting overlapping waveforms that clashed and merged in ways defying known physics. Dr. Sofia Alvarez, who led the analysis at the University of Cape Town, described the data as listening to an orchestra tuning its instruments, except every musician is playing a different song in a different key at the same time, and somehow it works. What makes these storms so unsettling is their paradoxical structure. Chaos theory suggests such overlapping signals should degrade into white noise, a featureless hiss. Yet spectral analysis reveals eerie order beneath the surface. In 2022, AI algorithms parsing the data isolated recurring fractal patterns, tiny bursts nested within larger ones, each mirroring the other's waveforms like Russian nesting dolls made of sound. The odds of this occurring naturally, less than 1 in a billion. Some researchers point to the star's extreme convection currents, bubbles of plasma larger than solar systems, as potential culprits, their collisions generating shock waves that sculpt radio emissions into these unnatural shapes. Others, like Dr. Linus Carter at Caltech, propose a radical alternative. Stephenson 218 shear mass might be warping spacetime so severely its own signals ricochet back into themselves, creating feedback loops that amplify and repeat certain frequencies. But the most haunting detail lies in the storm's timing. In 2023, the European VY network caught a fleeting moment of coherence, a 2-second interval where all overlapping signals briefly synced, their waveforms aligning into a near-perfect Bessel function, a shape often used in human-engineered antennas to focus radio waves. Natural processes don't produce such precision. The event lasted barely a blink, but its implications linger. Could Stephenson 218 chaos be a veil, a cosmic smokescreen hiding something far more deliberate beneath? As the hypergiant continues its tempestuous broadcasts, one truth becomes clear. This isn't just noise. It's a puzzle wrapped in a storm, a riddle whispered at volumes that shake the galaxy. And with every eruption, Stephenson 218 challenges us to reconsider not just how stars communicate, but what they might be trying to say. From the eerie, rhythmic pulses of VY Canis Majoris to the hauntingly precise echoes of HR 5171A, these 25 signals from Hypergiant Stars defy all expectations. Each one is a cosmic riddle wrapped in layers of plasma and magnetism, a phenomenon that bends or outright shatters our understanding of how stars behave. Some whisper in mathematical codes, others scream in chaotic dissonance, and a few seem to react to our observations as if aware of our gaze. But taken together, they paint a picture of the universe far stranger than we ever imagined. One where stars don't just shine, they communicate in ways we're only beginning to decode. What ties these signals together isn't just their mystery, it's their defiance. Time and again, nature reminds us that the laws we've etched into textbooks are more like suggestions in the face of such extremes. Eta Carinae's artificial seeming bursts, NML Cygni's harmonic Fibonacci sequences, KW Sagittarii's encrypted pulses, each one feels like a deliberate challenge, a gauntlet thrown down by the cosmos. Are we witnessing the birth of undiscovered physics, the flickering remnants of hyper-advanced civilizations, or something even more unsettling, a universe where the line between natural phenomenon and engineered signal doesn't just blur, it vanishes entirely? The most tantalizing question isn't what these stars are broadcasting, it's why. Consider Westerlund 1 synchronized chorus, or GSER's 7 laser-like beams targeting cosmic nurseries rich in life's building blocks. Coincidence possibly, but when a pattern repeats across dozens of hypergiants scattered across the galaxy, it's hard to dismiss the nagging suspicion that we're missing a fundamental piece of the puzzle. Even the skeptics admit these signals share an uncanny kinship with the very technosignatures we've long theorized might betray alien intelligence, yet perhaps the truth lies beyond even that. V838 Monocerotes looping echoes, Stephenson 218 controlled chaos, Rho Cassiopeia's silent gamma screams. These aren't just anomalies, they're glimpses into a reality where stars might not be mere objects, but participants in processes we can't yet fathom. Could hypergiants be cosmic transceivers, their immense energy harnessed by forces natural or otherwise, to send messages across time and space? Or are we simply hearing the universe's raw syntax, the unfiltered language of matter and energy at their most extreme? This is where you come in. The beauty of these mysteries lies not in their answers, but in the questions they ignite. Maybe you think why Scutti's delayed bursts betray hidden dimensions, or that S. Doradus's observational shyness hints at quantum awareness. Whatever your theory, the cosmos is listening. Drop your wildest ideas in the comments, because history shows us the next great leap in understanding often starts with a whisper. And right now, the universe is screaming.